All right, guys, so we are on example 16.4 now. Two styrofoam balls of mass 10 grams each are suspended by threads of length 25 centimeters apart. The balls are charged, and they're hanging apart, and it gives you the angle of 15 degrees. So I would have had you do a lab similar to this with balloons, and we would have charged them and suspended them from the ceiling, and we would have had to have figured out the charge of these as well. All right, there are three parts to this. Part A and B are pretty simple. Part C is the mathematical one. So this says, are the signs of the charges the same or opposite? So I think I actually have like a little, thing over here, a couple slides away. So if they're apart, what do you think? Well, if they're apart, then they're the same charge. We don't really know if they're positive or negative. We just know that they're the same charge. Okay, part B says, are the magnitudes of the charges necessarily the same? We don't really know, but because whenever you charge it, you could have gotten more electrons, on one versus the other. But basically Newton's third law. For every action, there's an equal and opposite reaction. So basically states that the forces are equal in magnitude and opposite in direction. Okay, so the forces are going to be the same. It's going to be in opposite direction. It's kind of like if I walk on the earth, my mass and the earth's mass are different, obviously. So, but, the earth doesn't push up on me any more than I'm pushing down on it when I'm walking. Okay? So part C, let's go back to the question. It says, find the net charge on each ball, assuming that the charges are equal. Okay, so what we need to do is, I'm going to draw sort of like a free body diagram really quick. Not really a free body diagram, more like a model of what's happening. So you've got these two styrofoam balls, and then it kind of drew this picture going down. And it said that each of these angles were 15 degrees. Okay, now, if we think about it, as far as our X and our Y components are concerned, if you're suspending something from a string, then there's going to be tension involved. So remember, tension was one of the forces that we discussed. So let's just take this one right here, for example. There's going to be a force that's pulling down. That's weight. There's going to be an electrostatic force going this way. Why is it going to the right? This one's going to the left. Because they're the same charges. Let's just say they were positive. They would be repelling, right? So they'd be pushing against each other. And then you have this force right here. Let me see if I can figure out a different color for a minute. Yeah. So you've got this force going like this. This is tension. Okay? So you've got lots of different forces that are happening. So we need to break them up into X and Y components. So if we do our forces in the X direction, we have our electrostatic force minus our tensional force. Now, think about this. The tensional force right here has both Y. If you broke this up into, let me change the color again. If you broke this up into, like, let's say this was your coordinate system, and this was the origin right here. Okay, so you've got your tension in the Y direction, and you have your tension in the X direction. Okay? And this angle right here is equivalent to that angle right there. All right, so now let's think about that. If we have, we're in the X direction, so think right here for a minute. It's opposite to the angle. So what do you use if you're opposite to the angle? Use a sine. Okay? And all of this is in equilibrium because after they've repelled, they're just sort of sitting there, like in this suspended position at an angle of 15 degrees. Okay? So it's all in equilibrium, which means that it's equal to 0. And then you do the same thing for the y of x. Or, sorry, not the y of x, the force of y. So you've got your tension still, right? You've got tension that's going in the y direction now. And it is, you could either look at it like over here, or you could look at it over here. It's really whatever. But it's going to be positive because it's going up, and it's cosine theta. And you also had this weight that's going down, so weight, okay? So something like that. Remember, whenever you're doing weight, though, it's mass times gravity. Okay, so I'm just breaking that down a little bit farther. All right. Now, electrostatic force. We are not looking for the force. We are looking for the charge. So which letter are we looking for? What is the symbol for charge? The symbol for charge is Q, right? So if you go back to Coulomb's equation, he had K times Q1, Q2 over R squared. All right, now we are saying that the charge here is equal, okay? Because of the force being equal. And so for this, we can say like that, okay? And we really need to figure out what, the force is, right? The electrostatic force. But we also are trying to ultimately find Q. Okay, so whenever we go to solve for Q here, we're going to end up like this. We're going to end up doing the square root of all of that. Okay, so, all right. Now, I've got to figure out how to find electrostatic force. So let me go back up to these two equations right here for a minute. Okay, so I'm going to rewrite those. I'm going to rewrite those down here a little bit. So I'm going to take the electrostatic force and I'm going to move this tension over. So it'll end up being tension sine theta. Okay, so I just added that over to the other side, like that. And you can do the same thing and have your, now, I want my tensions on the same side of the equation, okay? So if you move this over, you would technically have to subtract it. So then you would have negative weight minus or equal to negative tension. So let's just make the signs positive instead of negative, okay? So we'd have weight is equal to tension cosine theta. Now, if I divide both of those, what happens to the tension? It goes away. I have sine theta over cosine theta. Well, what's sine theta over cosine theta? It's tangent theta. So it's like this. Sine over cosine is tangent. All right? Which you got to remember that weight is mass times gravity. Okay, so I could move mass times gravity over, and I would have that the electrostatic force is equal to tangent theta times mass times gravity. Okay? All right. So that's the electrostatic force. Do we have theta? Yes, we know that it's 15 degrees. Do we have mass? Yes, we know that those styrofoam balls are 10 grams. Do we know gravity? Yes. So we could actually find electrostatic force now. Okay. Now we can also do, we've got to figure out, we know K because it's a constant. We just figured out how to find electrostatic force. How do we find R? All right, so we got to look back at our diagram for a minute up here. And I'm going to change colors again. So for R, we know that the string, because it told us in the problem a couple slides back, was that this string right here was 25 centimeters. So we need to figure out this entire length right here. Well, if we were going to hang that string like straight down, right, that would be 25 centimeters still. So basically we have got this string and this string. So we've got two of those strings. Okay, times 25 centimeters, but this is in the X direction. Okay, so 25 centimeters sine, because X here is opposite to this angle. So sine. If it was close to the angle, if it was adjacent to the angle, then it would be cosine. So sine 15 degrees. If you solve that, you get that this is 12.9 centimeters. Okay, so this total distance right here is just 12.9 centimeters. It's not that far. All right, so now you can actually plug all of this stuff into this equation. So you've got, I'm just going to make it a different color. So you've got charge is equal to the square root of the electrostatic force, which we didn't actually solve yet, tangent of 15 degrees times 10 grams, so we need to make that into kilograms, times 9.8 meters per second squared, okay, times r squared, so we just figured that to be 12.9 centimeters, so let's go ahead and make that into meters. So 0.129 meters squared divided by K, which is 8.99 times 10 to the 9th Newton meters squared per coulomb squared. Multiply all that and do the square root, and you should get 20, or sorry, not 22, but 2.2 2.2, my hand keeps hitting that next button, I guess, times 10 to the negative 7th. Or you could say, and this is all in coulombs, by the way, or you could say 0.22 microcoulombs. Kind of wants you to start recognizing how to convert into those simpler, instead of having those exponents, it wants you to put them into micro and stuff. And I'm not saying that you will necessarily have to, you don't have to do that, but for homework purposes and stuff, it might make you answer it in things like microcoulombs. Okay? So this was example 16.4. I hope that this makes some sense. If not, go back and watch it over again. If you're not understanding like why I'm getting sine instead of cosine, those are things from back in vector addition. So just have to remember, if they're adjacent, then it's cosine. If they're opposite, so like for instance, this X right here is opposite to this angle. So that's why I had to do sine, okay? And this was just one triangle right here. So that's why I had to multiply it by 2, because I'm actually doing 2 of those, okay? All right, so anyway, that's example 16.4, and I'm going to stop it and we'll go on to the next one in the next video.